Okay, we're just going to finish up lesson 40. We were talking about the general form of the power rule for logs. That is log base b of m to the n power is equal to n times log base b of m. So if you have an exponent on the argument of a log, you can just bring that exponent to the front of the log. So log base b of m to the n is equal to n times log base b of m. So we did that first one on the left. On the right, we've got log base 12 of x is equal to 2/3 log base 12 of 64. So you've got log base 12 of x is equal to, then you've got this coefficient in front of the log. You can take that and put it into the exponent of the argument. So that would be log base 12 of 64 to the 2/3 power. So log base 12 of x is equal to log base 12 of 64. The cube root of 64 is 4, and then you square it, and that's 16. So if these two logs are equal, they have the same base, that means their arguments are equal, so x is 16. And if you go back and look, if you put in 16 for x right there, it is not going to give you a negative argument, so you're good. X is 16, and that is the solution. All right, we're going to talk about properties of inverse functions. So in lesson 32, we learned to find the inverse of a function by solving for x and then interchanging all the x's and y's. Inverse functions undo one another, which means that if you put x into one function and then put the result of that into the inverse function, you're just going to get back x again. So if f and g are inverse functions, then you take x, some member of the domain of g, and put it into the g function, and then g of x comes out. And then when you take that and put it into the f function, then that is f of g of x, and you get x. So if f and g are inverses, and you take some value of the domain and put it into the g function, you get g of x, and then you take that and put it into the f function, it's going to undo whatever putting it into the g function did, if f and g are inverses. So you put it into g, you get something out, you take that, stick it into the f function, it's going to undo what you did to it, so it'll just end up being x again. It'll go back to the way it was, just like multiplication and division are inverse functions. If you have a number like 2 and you multiply it by 3 and then you divide it by 3, it's just like you didn't do anything. It's the same is true about inverse functions. If you put a number into a function and then you take whatever you get and put it into the inverse of that function, you'll just end up with x again. Another way to understand this a little bit is if you have a function g that maps these numbers 3, 4, and 5 onto the numbers 6, 7, 8 like this. 3 becomes 6, put 4 in, you get 7, put 5 in, you get 8. If f is the inverse function of g, of course, it switches the domain and range. So now when you put in 6, you get 3 back. When you put in 7 to the f function, you get 4. When you put in 8 to the f function, you get 5. So this is what inverse functions are. G is the inverse of f. So for example, if you put 3 into the g function and you get 6, and then you take what you got and put it into the f function, you just get 3 again. So it goes back to what it started out to be. So this is the point of this, is that if you want to check and see if two functions are inverses of each other, all you have to do is take the composition of the two functions. F of g of x should equal x, and g of f of x should also equal x if the functions f and g are inverses. So let's look at an example. So, all right, so show that f of x is equal to 1/3 x minus 3 and g of x equals 3x plus 9 are inverse functions by computing their compositions. So what we're going to do is we're going to do f of g of x, see what we get for that, and then we're going to do g of f of x and see what we get for that. So f of g of x, you're going to take the g of x function and put it into the f function. So the g of x function is 3x plus 9. So I'm going to take that and put it into the f function. Wherever I see an x, I'm going to put 3x plus 9. So f of 3x plus 9 is going to equal 1/3 times 3x plus 9, and then minus 3. That's x plus 3 minus 3. That is x. So when you put x into the g function, and then you take that and put it into the f function, you just get x back again. So that would indicate that f and g are inverses, but we have to make sure it works both ways. So g of f of x is going to be g of 1/3 x minus 3. That's what f of x is. And so that, you take 1/3 x minus 3 and put it into the g function, wherever you see an x. So that's going to be 3 times 1/3 x minus 3 plus 9. And that is 1x, or just x, minus 9 plus 9, which is x. The two functions, g and f, are inverses. Okay, so here we want to show that f of x equals 1/x minus 3 and g of x equals 3x plus 1/x are inverse functions by computing their compositions. So we are going to do f of g of x and see if that equals x, and then g of f of x and see if that equals x. So f of g of x is f of 3x plus 1/x. So I'm going to take 3x plus 1/x and put it into the f function, which is going to be 1/3x plus 1/x minus 3. And that is, if we multiply this whole fraction by x over x, that'll get rid of that little fraction. So the numerator will be x, denominator will be 3x plus 1 minus 3x. So that is x over 1, which is x. That works. All right, g of f of x is going to be g of 1/x minus 3. So I'm going to take the g function, and wherever I see an x, I'm going to put 1/x minus 3. So that's going to equal 1/x minus 3. Whoops, sorry. So that is going to equal 3 times 1/x minus 3 plus 1 over 1/x minus 3. So this time I'm going to multiply this whole fraction, top and bottom, by x minus 3. So when I distribute that, the first term, the x minus 3, is going to cancel, and I'll just have 3. And then 1 times x minus 3 is x minus 3. And then on the bottom, I'm just going to have 1. The 3's cancel, and I end up with x over 1, which is x. So yes, these are inverses. So lesson 41 is only 3 slides, so I figure we can probably handle that. Reciprocal trig functions, the reciprocals of sine, cosine, and tangent, have their own names. They are cosecant, secant, and cotangent. So 1/cosine theta is called secant theta. And that is equal to hypotenuse over adjacent. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. 1/sine theta is called cosecant, which is CSC of theta. And that's hypotenuse over opposite instead of opposite over hypotenuse. And then 1/tangent is cotangent theta. And that is adjacent over opposite instead of opposite over adjacent. The only tricky thing here is that the reciprocal of sine is not secant, it is cosecant. That's a little bit tricky because you would expect 1/sine to be secant and 1/cosine to be cosecant, but that is not the way it is. The way it is that 1/cosine theta is secant theta and 1/sine theta is cosecant theta. So that's a little bit tricky. Okay, so if we take a look at this first one, we want to evaluate secant of -30 plus cotangent of 120. And so what that means is 1/cosine -30 degrees plus 1/tangent 120. And so we can find where we're going here. So if with -30 degrees, we're going clockwise 30 degrees into the fourth quadrant. And we can see that the x-coordinate there is square root of 3/2. So that is going to be the cosine of that angle. So we have 1/square root of 3/2, which is just 2 over the square root of 3. Then we have 120. So we go counterclockwise to 120, which puts us there. And tangent is y over x on our unit circle. So 1/tangent will be x over y. So it's going to be -1/2 over square root of 3/2. And so that is going to be 1 over the square root of 3, or so it's 2 over the square root of 3 minus 1 over the square root of 3. And that is going to just be 1 over the square root of 3, which is square root of 3 over 3. Okay, let's look at this one. We have secant 10 pi over 3 plus cosecant negative 7 pi over 2. So what does that mean? That means 1 over cosine 10 pi over 3 plus 1 over sine negative 7 pi over 2. And so to figure out where we go for 10 pi over 3, we can remember that pi over 3 is 60 degrees, and so 10 times that is going to be 600 degrees. So we have 1 over cosine 600, and then for that we go all the way around the circle, 360 plus another 240, and that puts us at 600 degrees. So that is 4 pi over 3. That is negative 1/2 negative square root of 3 over 2. So we're looking for the cosine, which is the x-coordinate. So it's 1 over negative 1/2, which is just negative 2 for that. Now we look at the other term there, 1 over sine negative 7 pi over 2. And pi over 2 is 90, so 7 pi over 2 is going to be negative 7 times 90, which is negative 630. So that is sine of negative 630. And to get that, we go, this time we're going to go clockwise all around the circle once, plus another 270. And so that puts us there where sine is 1, because that's the y-coordinate. And so that is going to be just 1 over 1. And so we have negative 2 plus 1 is negative 1. Okay, let's look at the other two. We've got 2/3 cosecant negative 135 minus secant 135. So that's 2/3 times 1 over sine negative 135 minus 1 over cosine 135. So we're looking at negative 135. So we're starting at 0. We're going to go clockwise 90 plus another 35, which puts us right here. Sine of that angle is negative square root of 2 over 2. So we've got 2/3 times 1 over negative square root of 2 over 2. And in this situation, it's probably better to just call it 1 over the square root of 2. When you're using the inverse functions, I mean, I always rationalize these, but you could just write it as negative 1 over the square root of 2, negative 1 over the square root of 2, and that way you can just flip it. So 1 over sine negative 135 is 1 over negative 1 over the square root of 2. And then cosine 135, you start at 0, go counterclockwise, brings you here, and you're going to have 1 over negative 1 over the square root of 2. So 2/3 times negative square root of 2 minus negative square root of 2. So 2/3, well, this is going to be plus. So 2 square root of 2 over 3, negative 2 square root of 2 over 3, plus the square root of 2. If we get a common denominator and add, we're going to have negative 2 square root of 2 plus 3 square root of 2 over 3. And that will give us just the square root of 2 over 3. This next one, we have cotangent 17 pi over 6 and minus the square root of 6 times cosecant negative 9 pi over 4. This one, I'm just going to not change it to degrees. So 17 pi over 6 is the same thing as 2 and 5/6 pi. So 2 pi is all the way around the circle one time. And then we're going to go another 5 pi over 6. So pi over 6 is 30. So 1, 2, 3, 4, 5 puts us right here. So that is where we're looking for the cotangent. And cotangent is going to be x over y. So we have negative square root of 3 over 2 over 1/2. And then we've got cosecant negative 9 pi over 4. So 9 pi over 4 is 2 and 1/4 pi. So 2 pi is all around the circle once, and we're going clockwise this time. So all around the circle once, and then we have an extra pi over 4. So we're still going clockwise, so we will end up here. and we're looking at cosecant. So square root of 6 times 1 over the sine of that. So sine is the y-coordinate, so negative 1 over the square root of 2. So we have negative square root of 3 over 2 over 1/2 is just negative square root of 3. So that is plus square root of 6 times square root of 2, which is negative square root of 3 plus square root of 3 times square root of 2 times square root of 2. So that is just negative square root of 3 plus 2 square root of 3 is square root of 3. All right, we have permutation notation. The standard notation for the number of permutations or arrangements of n things taken r at a time is p with parentheses n comma r. But our textbook doesn't use that. It uses a different one. And that is a p with a little n in front and a little r behind. So if we wanted to figure out how many permutations there are of 22 things taken 6 at a time, that means you've got 22 things and you want to know how many arrangements you can make of 6 of those things. If you have all 22, you're going to take 6 at a time and make an arrangement. And you want to know how many possible arrangements could you do. So that's basically saying, all right, I have 6 spaces to fill, and I'm choosing to fill them from these 22 things I have. So for my first choice, I have 22 possibilities, and then 21, and then 20, then 19, then 18, then 17. So that is the number of permutations of 22 things taken 6 at a time. So let's take that and write it in a more simple way. We've talked about how you can use factorial notation to write something like this in a more simple way. So if you have 22 times 21 times 20 times 19 times 18 times 17, that's the same thing as 22 factorial, but you don't want all the 16, 15, 14, 13. So you're going to divide it by 16 factorial, and that gets rid of 16, 15, 14, 13, and all that, and you're just left with 22 down to 17, which is what you want. So this means the same thing as that. So let's see if we can use that to figure out a more general expression for the number of permutations of n things taken r at a time. So if you have n things, like up here we had 22 things, and the expression for counting had 22 factorial in the numerator. So if we have n things, we'll put n factorial in the numerator and then take an r at a time. Well, in this particular specific problem, we were taking them 6 at a time, and we ended up with 16 factorial on the bottom. So that 16 factorial, how did we figure that out? Well, we had 22 total, and we're taking it 6 at a time, so maybe it's 22 minus 6. 22 minus 6 is 16. So that is where the 16 comes from here. So that's where it's going to come from in the general expression also. All we have to do is do n minus r factorial. So this is a general expression for how to find the number of permutations of n things taken r at a time. So if I want to find the number of permutations of 12 things taken 4 at a time, I can just put it into this expression. 12 factorial over 12 minus 4 is 8, so 8 factorial. So that is 12 times 11 times 10 times 9. And that's what we would have gotten anyway. But if we had a huge number of things, taken a huge number of things at a time, we wouldn't want to have to sit there and figure that out. We would just want to punch that into the calculator. So we don't actually have to write that. We can just take our calculator and hit 12 factorial divided by 8 factorial. And that would give us however many possible permutations there are of 12 things taken 4 at a time.